Hi guys, in the last lecture we covered the transient analysis of a power system. In the transient stability analysis we saw various cases relating to different kind of faults, and we were concentrated on determining the critical clearing angle, that is the maximum angle at which the fault can be cleared, and we translated that result into critical clearing time, which was the maximum time at which a fault can be cleared. So in this lecture what we will do is, we will be focusing our attention to a few gate problems that have come from this topic. So let us get started with the first problem. It is saying the inertia constant of 100 MVA 50 Hz 4 pole generator is 10 megajoule per MVA. So it will be H is 10 megajoule per MVA. Okay, I have determined H because of the units. Now mechanical input is suddenly raised from 50 to 75. So let me say PM1 is 50 megawatt and PM2 is 75 megawatt. Now before raising the mechanical input, the system would be in steady state, that is PM would be equal to P. So PM1 was equal to P naught, which is equal to 50 megawatt. Now PE is actually related as P max sine delta. So since PE depends entirely on delta, PE cannot change instantaneously. Okay, PE can only change as the delta will change. That means it can change gradually. Now it is asking the rotor acceleration. So I can assume that PE remains constant at 50 megawatt. So applying swing equation, I have taken 180 because I am applying in per unit and in electrical degree. So 75 is PM, 50 is PE, upon base is 100 because power must be in PU. So it is 0.25. From here calculating d square delta by dt square. Point 0.25 into 180 into 50 by 10, which comes out to be 225 electrical degree per second square. Okay, this will be the rotor acceleration. So I have assumed that we are calculating the initial rotor acceleration, that is the rotor acceleration at the time of fault, because after that delta will change, due to which PE will also change. So it will be difficult to determine what is the value of PE. In our next problem, it is saying a synchronous generator is connected to infinite bus through a lossless double circuit line. So system is like this. Generator is delivering 1 pu power at a load angle of 30 degree. So it is saying before the occurrence of fault, PM is equal to P is equal to 1 pu and delta naught is 30 degree. Now a sudden fault reduces the peak power that can be transmitted. Peak power that can be transmitted is P max. But after the fault, P max is actually P max 2. Okay. Now after clearing the fault, maximum power can be transmitted is 1.5. So P max 3 is 1.5 pu. We need to find critical clearing angle. Now delta CR is given as cos inverse PM delta max minus delta naught P max 2 cos delta naught plus P max 3 cos delta max divided by P max 3 minus P max 2. Here delta max is given as 180 minus sine inverse Pm by P max 3 that is 180 minus sine inverse 1 by 1.5. So how much will this come out to be? 138.19 degree. So delta CR will be cos inverse, PM is actually 138.19 minus delta naught is given as 30, but this should be in radians. P max 2 is 0.5 cos 30 plus 1.5 cos 138.19, 1.5 minus 0.5. So this angle will come out to be 70.29 degree. So this is the maximum angle at which the fault can be cleared. You can clear the fault before this, but not after this point of angle. Okay. In our next problem, it is saying a generator delivers 1 pu power to an infinite bus through a purely reactive network. That means PM is equal to PE is equal to 1 pu, because it is talking about steady state. The maximum power that could be delivered by generator is 2 pu. So P max 1 is 2 pu. A three-phase fault occurs at the terminals of generator, which reduces the generator output to 0. If generator output becomes 0, then P max 2 is 0. The fault is cleared after Tc second. So T is equal to Tc, fault is cleared. The original network is then restored. That means after the fault, conditions are same as before the fault. That is 2 pu. It is saying where the maximum swing of rotor angle delta max is 110 degree. We need to find delta C, that is the rotor angle at T is equal to Tc. Now suppose if we were talking about critical clearing case. If we were talking about critical clearing case, then first of all, what will be my delta naught? That will be sine inverse PM by P max, that is sine inverse 1 by 2, that is 30 degree. So what should be delta max? Pi minus delta naught, which is 150 degree. I am directly using these formulas because I know this is a case which corresponds to fault near the bus for a single transmission line. That was our second case that we analyzed for the transient stability analysis. But now delta max given to us is less than 150. That means it is not a critical case. It is a general case in which the system is stable for delta max is equal to 110. The critical clearing angle we were determining like cos inverse delta max minus delta naught plus P max cos delta max over P max. This same formula is applicable here also, just delta max will not be equal to 150. Rather, we will take it as 110. PM is 1. Delta max is 110 minus 30 into pi by 180 plus P max is 2 cos 110 divided by 2. So this will come out to be 69.14 degree. Okay. So that is your clearing angle. It is, though it is not the critical clearing angle. For critical clearing, you have to keep delta max equal to 150 degree. Okay. So whatever formula we have seen for TCR and delta CR can be applied for delta C, which is any clearing angle, and TC, which is the clearing time, though they may not be the critical values. In our next problem, it is saying a generator feeds power to an infinite bus through a double circuit transmission line. A three-phase fault occurs at middle point of one of the lines. Okay, so this is a general case. The infinite bus voltage is 1 pu. The transient internal voltage of generator is 1.1 pu. The equivalent transfer admittance is 0.8 pu. Okay, so this is given during the fault. So during fault I can calculate P max to, that will be 1.1 into 1 into 0.8. So it will be 0.88 pu. Okay. Now the 100 MVA generator has inertia constant 5 and it delivers 1 pu power, that is Pm is equal to 1, Pa is equal to 1 pu prior to the fault. Since before the fault it is talking about, so we are taking Pm is equal to P because it will be under steady state. And rotor power angle of 30 degree. Okay. We need to find initial accelerating power. In this case, however, my power angle curves, this was before the fault and this was during the fault, this was after the fault. Then we took Pm, so this was equal to delta naught. So as soon as the fault occurred, Pm was this much only, but P reduced to this. So as the fault occurred, P became P max to sine delta naught as we fell from point A to point B. So it will be 0.88 sine 30, which is equal to 0.44 pu. But Pm is actually 1 pu. So accelerating power will be Pm minus Pe, that is 0.56 pu. But why it is asking only initial value? Because as the time passes we will go from B to C. So due to which our electrical output will change. Since the electrical output is changing, the accelerating power will also change. That is why it is only asking about the initial value. In the next problem, which is a part of the same problem, it is saying we are given that initial accelerating power is x pu. We need to find initial acceleration in electrical degree per second square and inertial constant in megajoule second per electrical degree. So this constant here refers to m. Now m had two formulas, gh by pi f, which will give the units megajoule second per electrical radian, or m is equal to gh by 180 f, which will give in megajoule second per electrical degree. Okay, so we will use gh by 180 f because the unit is megajoule second per electrical degree. So G is actually the rating, 100 MVA. H is given as 5 megajoule per MVA upon 180, frequency will be 50. So this will be 1 by 18 or 0.056. So this will be the inertial constant m. Now it is asking about initial acceleration. The unit are given as electrical degree per second square. So the swing equation will be h by 180 f d square delta by dt square Pm minus P, which is equal to Pa. So d square delta by dt square is, Pa is given as x into 180 into 50 by 5. So it will come out to be 1800x electrical degree per second square. So that will be your initial rotor acceleration. Okay. So you have to make sure you use the correct version of swing equation based on the problem. Just by looking at the units, you have to judge which swing equation to use. In next problem, it is saying, consider a synchronous generator connected to infinite bus by two identical parallel lines. The transient reactance X of the generator is 0.1 pu. Steam input is constant at 1 pu. Now, due to some previous disturbance, rotor angle is undergoing an undamped oscillation, which is shown here with a maximum value 130 degree. Now, one of the parallel line will trip due to relay maloperation. Now, when one of the lines trip, the value of X equivalent will be 0.1 plus X. Before the line trips, the X equivalent would be 0.1 plus X upon 2. Okay, the line is tripping when delta T is 130. We need to find maximum value of X so that we do not lose synchronism. Now, before the fault, suppose my power angle curve looks something like this. Now, when the relay maloperates and the line is removed, the reactance increases, due to which Pmax will reduce. So, my curve will become something like this. Now, Pm is given as 1 pu. Okay. Now, it is asking what is the maximum value of X at which the system does not lose synchronism. Now, earlier when the oscillations were going on, they were going on up to 130 degree. We know the system will lose synchronism if we go beyond this point. So, this point must correspond to 130 because this is the maximum point in the rotor oscillations. So, this will form the critical case. So, let me call it as delta X. So, now if delta X is equal to 130, this will be my critical case. But if delta X is less than 130, that means you will fall in this region 130. And since you are entering this region, system will become unstable because we cannot go beyond delta X. If delta X is greater than 130, that means you are lying here. So, system will be stable. Now, delta X we know in this case will be 180 minus this angle, or 180 minus sine inverse Pm by Pmax 2. That is 180 minus sine inverse Pm is 1, Pmax is E into V. Pmax 2 will be EV by X, that is 1 into 1 by 0.1 plus X, that will be 130. If we simplify this, it will be 50 is equal to sine inverse 0.1 plus X. So, here X will come out to be how much? If we calculate sine 50, it will be 0.66 pu. Okay. So, that is how my system will not lose synchronism if you fall at the point of critical point or at the maximum angle, if delta max is equal to 130 degree. Let's move on to the next problem. It is saying a transmission line has a total series reactance of 0.2 pu. Okay. Then reactive power compensation is applied at the midpoint of the line like this. So, here reactance will be 0.1 pu, 0.1 pu, such that midpoint voltage of transmission line is 0.98. Okay. If voltage at both ends of the line is 1 pu. We need to find steady state power transfer limit. So when we studied about SVC, I told you that SVC does not inject or does not consume any real power from the line. So whatever is the real power coming from sending to midpoint will be same as the real power going from midpoint to the receiving end. That means if we calculate between sending and the midpoint, that will be my power capability. So Pmax will be 1 into 0.98 and the reactance is 0.1, which is equal to 9.8 pu. So this will be the maximum power transfer limit of the transmission line. So that is why SVC was increasing the power transfer capability of the system. Do not go on and directly apply the power transfer equation between Vs and Vr. Why? Because SVC will inject reactive power. So reactive power will not be same between Vs and Vr. So you have to apply between the sending end and the midpoint, or from midpoint to the receiving end, and then take minimum of the two values. Coincidentally, the two values here will become equal, because even if you calculate between the midpoint and the receiving end, it will come out to be 9.8. But otherwise, suppose one value was 6 pu, other was 10 pu. So it says that the maximum power capability in one section is 6, other is 10. If you keep Pmax as 10, then you may be violating this limit, which will make the system unstable. So we will keep Pmax as minimum of the two values so that both sections of the lines are stable. Okay. So you will calculate two limits, one from sending to midpoint, other from midpoint to the receiving end, and then take minima. In our next problem, it is saying a 500 megawatt 21 kV 50 Hz 3-phase 20 pole synchronous generator, rated power factor 0.9 and moment of inertia is given. H it is asking. We know GH is equal to kinetic energy, which will be half J omega Sm square. So let us calculate kinetic energy first. J is 27.5 into 10 raised power, this should be 3, 10 raised power 3 into omega Sm. Omega Sm is, how to calculate omega Sm? Omega Sm is actually 2 by P into omega Se. Omega S is actually 2 pi F square. So half into 27.27 500. Let me write. How many poles are there? 20 pole. 2 into pi into frequency is 50. So this will be half into 27 500 into 10 pi square. This is kinetic energy. Now H will be this divided by G. G is actually, G is the MVA rating, but we are given the power rating, not the S rating. So how we will calculate? That is power by power factor, that is P by cos phi. So it will come out to be 2.44 second. Why second? Because megajoule per MVA will have the units of second. Energy by power is time. In the last problem, it is asking a large synchronous generator is feeding power to infinite bus at slightly lagging power factor. If a total loss of field occurs, that is EF becomes 0. The system can supply sufficient reactive power without a large terminal drop. Now if EF becomes 0, P becomes 0, due to which Pm minus P becomes greater than 0, and d square delta by dt square will become greater than 0. So rotor will accelerate, due to which Nr will become greater than Ns. If such a thing happens, then it runs as an induction generator, because in induction generator slip is actually less than 1. Sorry, slip is actually negative, because slip is Ns minus Nr by Ns. this will be less than 0. But the problem with induction generator is, since there is no field excitation, we have to generate the flux by drawing magnetizing current from the supply. So it will draw an additional current from the supply, which is magnetizing current. Due to the additional current from the supply, the stator will get overheated. Hence, we will have to trip it after certain time. Otherwise, the stator will get overheated in an induction generator. So it will be answer C. Okay, why we are tripping? Because otherwise the stator gets overheated. So these sort of problems can be framed from the stability topic. Here the transient stability is most important. You have to remember the swing equation and the equal area criteria. Okay, so this is all from the unit of stability.